Hello. In this example, we will talk about normal stress, shearing stress, and factor of safety. So we have a design like this, and we have a force that is applied on the shank down. That's P equals 6 kilonewton, 6,000 Newton. And we know that the maximum, the ultimate stress in the bolt is 30 megapascal and in the plate 20 megapascal. And the question is it safe? Is it safe if we want a safety factor of 2? Okay, so we don't want to reach 30 megapascal, basically we want to reach only 15. So we have some um, offset with the ultimate. So remember the factor of safety equal the ultimate stress divided by the allowable stress. So if the factor of safety is 2 and the max is 30, the allowable stress must be no more than 15. So we need to calculate them and see if we are under that. Okay, let's work on that. So there is 4 different scenarios to check. First, let's check that the normal stress, normal stress in the bolts are below the 30 megapascal. Okay, let me rewrite the dimensions. So the bolt height is 35 millimeters and the bolt diameter is 20. The bolt head thickness is 7.5, this one there, and this one is 10 millimeter. I think you see it a bit better. This one is the diameter and this one is the diameter. So number 1, let's make sure that I have some space. Yep, I cleaned that. I didn't clean it all the way there. So number 1, so we have the bolts like this, boop, 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 boop. So the normal stress, where they will be the larger, is it in the head or is it in the shaft? That will be in the shaft, in the shank, because it's smaller. So the sigma normal in the bolt will be equal to the force 6,000 divided by the area, and this is this area there, this area. So that will be the diameter, that will be pi times the diameter 20 divided by 2 square. So the sigma in the bolt will be 19.1 megapascal. And this is the allowable stress. Okay, we will compare with the safety factor at the end. Number 2, the normal stress in the plate. So we are doing this number 2. Okay, so the plate look ups like this. Okay, and there is a hole. And if we look at the where the normal stress apply, that will be all the way there, like, okay, there, all the way around on the plate. Okay, so we have the sigma for the plate that is equal to the 6,000 divided by these circles minus this circle, these circles in the area. We want to look just like the crown around. So the outside is pi times 35 divided by 2 square. This is the outside. I'm on this one. This is there. Like I try to find this one there. So it's this one minus this one inside. So minus pi, oh my God, pi times 20 divided by 2 square. So that gives us sigma of the plate, normal stress equals 9.25 megapascal. Okay. Number 3, we are looking at the shearing stress. Let's do inside the bolt. Okay, so shearing stress inside the bolt. So this bolt, like this, oops, okay, so there's the force all the way there that's applied vertically like this, all the way around. So the force P is spread all the way around that one. Does that make sense? And all the way around, like this. So the force is pushing there, there, there. Like, let's do this one like this. So the tau, some people say, the tau for the bolt will be the 6,000 divided by this area. So this area, that will be the circumference, so the diameter times pi, so pi times the diameter, the small diameter, the inside, that is 20, time the thickness of the head of the bolt, so 7.50. Oops, so this one will be the toe of the bolt will be 12.7 megapascal. And last one, we are looking at the shearing in the plate. Okay, so number 4. So we have the plate like this, and we have the head. Try to do that like this. Oops, this one is smaller. But where the shearing apply for the plate, it's there on the outside and all the way around for the plate. So that will be the toe. Bigger. The toe for the plate will be the 6,000 divided by the circumference of the outside, so pi times 35, and time, this way, the thickness of the plate, that is 10. So the toe of the plate is, this is 5.46 megapascal. Okay, so this is the force that, the stresses that the bolt and the plates will have if we apply a 6,000 force. And now the question is this safe? Okay, so we want to apply a safety factor of 2. Okay, so let's check. The bolt has an ultimate of 30 megapascal. The plate has an ultimate of 20 megapascal. Bolt, we say 30 megapascal. And this one 20 megapascal. So if we do the safety factor there, we will have 30 divided by 19.1, and this is equal to, let me find my value there. This is not safe. This is 1.6. This is 1.6. Not safe because this is not more than 2. This one, the safety factor, if we do the 20 divided by 9.26, 20 divided by 9.26 is 2.2. So this one will be safe. This one safety factor will be 30 divided by 12.7. So that will be 2.4. They will be safe. And this one, the safety factor will be 20 divided by 5.46. So that will be 3.7. That will be safe. So in our case, the only one that is not safe is the normal force in the bolt. So to remove that, we can increase the area of the bolt. We can increase the area of the bolt. Okay. So this is that for the safety factor and a good little mix-up of shearing stresses and normal stresses, and make sure to really look at the where you have the contacts between the two elements. Hope that makes sense. Bye bye.